The earliest ancient writings from Babylon and Greece describe tuning lyre strings using the method of tuning by concords, which is using all perfect fourths and fifths tuned by ear until they don't beat. So, for example, the E, a perfect fifth above our A 440, would be 660 hertz, which is 440 times 1.5. And then to find the B, you could go, it would be 3 squared, and that would be 9, but we have to drop it down into the octave we're interested in, which would be the 9 to 8 ratio. So powers of 2 don't do anything except change the octave. So the 8 just represents that you're dropping it 3 octaves. The ancient Greeks also realized that a stretched string could be measured and then divided according to these ratios, and so this was the invention of the monochord, a wooden box with a single string, and it was called canon in Greek. And it was noticed that by tuning by concords, you could produce a scale of all different notes until you reach the 13th note. There you get a note that's very similar to the one you started from, but just slightly off, and that little interval was called a comma. Today we call it the Pythagorean comma, and the ratio is a number that you can see in my text, but the important point is that it's 3 to the 12th power. That's what represents the Pythagorean comma. And it's about 23.5 cents, so it's about 1/4 of a semitone, roughly. And what I'll do is demonstrate with a graphic on my blog here how we derive this so-called Pythagorean tuning, and it's also known as 3-limit. So for the last interval, you'll hear that an augmented seventh is an anomalous name for that interval because it's nothing like a seventh. It's actually just smaller than the just a little larger, sorry, than the unison. And in fact, the tuning of A has not been 440 for very long. It varied as much as 400 to 456 hertz. So listen to the example.